This lecture presents a short introduction to association analysis within the lecture series on data analytics. Data analytics is concerned with various approaches to discover patterns from the data, and association analysis is a prime example of such goal or methodology. So association analysis is based on discovering interesting hidden relationships in large data which might not be obvious to us but might be represented by the evidence in the data which is hard to see. So an association rule would reveal a pattern between two attributes. Like, for example, if we have the market basket analysis, we can discover that if a shopper buys diapers, there is a high likelihood to buy a bread. This is just an example. So it is typical for market basket transaction, but also useful in various scientific disciplines such as bioinformatics, where we have huge data sets of genes and their expression data and their relationship to proteins, and we would like to mine and discover certain hidden relationships which might be important for general scientific discovery or drug design. Also, good examples are from medical diagnosis, because there could be various hidden patterns of indicating a certain disease which are not obvious, but the data might prove that there is a significant relationship between some manifestation and a particular disease. In various scientific data analysis workflows where big data plays a role, association analysis can be used very efficiently to form certain hypotheses, which can be then further analyzed to be proved or disproved. However, discovering patterns from large data is for human eyes prohibitive, and for computational power its sort of naive implementations are prohibitively costly, and because there are just so many rules which can be taken out from data, and many of the patterns are just spurious and insignificant. So we can analyze data, for example, like this market basket transaction, where we can see that we have certain transactions and we have the content of the market basket, where we see that we bought bread and milk. Another transaction was that somebody bought bread, diapers, beer and eggs, and so on and so on. The same representation could be also presented in the as asymmetric binary representation, where we can see that each transaction is encoded in this binary format and corresponds in and is equivalent to this tabular description. When we say that the association rule reveals pattern between attributes, the attributes are basically considered like these items in this market basket, where the attributes could be just one item, which is implying an association and likelihood of a purchase of another item, or it could be more items on both sides. And one item we can call a so-called one-item set. Two items we can call a two-item set, and k items, a set of k items, we can call k-item set. So item set is in this context a subset of items from the set of all items I, which are the all items, and they are collected from a set of all transactions T1 to Tn. So a k item set, as mentioned, is a set of k items. For example, like 3 item set is bread, milk, diapers, and a 0 item set would be an empty set. We have for our item set something which is called the support count. The support count describes how many times a specific item set X appears in all transactions, which is expressed by this sigma X, where through all transactions we go and we are looking how many times in these transactions this item set appears. Not just one of these elements, but for this 3 item set, it would need to contain the transaction all these 3 elements. So it means that if it will contain all these 3 elements, that it will also contain a 2 item set of milk and diapers, diapers and bread, or bread and milk and bread. And it will also contain therefore the 1 item sets of bread, milk and diapers. So we will use this item set for defining our implication rule, which will indicate what item set implies another item set, and that will basically formulate this association. Association rule is an implication expression of the form X implies Y, where the X and Y are disjoint item sets where the X intersection with Y is an empty set. So this is an implication that if somebody is purchasing X, then it is very likely that they will also purchase a Y. So, but this could be association rule could exist in many of these. Already here in this set of few transactions, we can have a lot of rules like bread to milk, bread, diapers, beer imply purchase of X, for example. We can see all possible combinations, and actually it's like I think around 600 rules even can be implied only from this super small transaction record data set. So therefore it is important that we define which of our items forming rules are these association rules which are actually somehow significant. So we need to quantify a strength of an association, and we will measure it by a key 2 characteristics, where one is called support and the other one is called confidence. And the support simply measures how often is a rule applicable to a data, and it basically measures that if we have X and Y in our data record, then how many times does it occur? So this is basically the sum of all transactions which contain both X and Y. So here, if we are looking, for example, for the bread and let's say milk, this would appear 1, 2, 3 times, and not here and not here. So that means that we will have 3/5 support. If we are looking for a support of a rule where based on milk, diapers, and bread, so where we are seeking for the rule of milk and diapers imply bread, this can be supported by milk, diapers, bread, milk, diapers, 2 out of 5 of the transactions contain it. So 2/5 is the support. So this could be a parameter to our association analysis. How big support do we want to have for our association rules? The second is expressing the confidence. How frequently does Y appear in transactions that contain X? So now we are looking at all transactions of X. So let's say if we have the milk, diapers imply bread type of rule, where the X will be milk and diapers and Y will be bread, then how many times is milk and diapers in our transaction record? Milk and diapers is 1, 2, 3, 1, 2, 3 times, and the milk diaper bread is 2 times, so 2/3. So we are quite confident about this rule, although it doesn't have too strong of a support. Generally, we would like to have confidence above 50%, and we would like to have rules which have a reasonably strong support, maybe at least something like 20%. It starts to be interesting, but probably even more. We can formulate an association rule mining problem as a problem to find all rules having support bigger than some minimum support threshold, and which has at the same time confidence which exceeds the minimum confidence threshold. So because there are many associations we can make from such a transaction record, for example, or from the other cases, but we only want to have the significant ones. As I mentioned, from these 5 transactions which have been shown, we can actually span a huge 602 different association rules. So, which is a huge amount, and only if we, for example, look at the ones which have the minimal support of 20% and the minimal confidence is at least 50%, 80% of these rules will be already discarded. So out of this 602, we will be the remaining, I don't know, something like about a little bit above 100 rules will remain after just these highly conservative numbers. So, but we can, for example, take some strategy how we can minimize this huge rule set, so that we just look at and analyze the rules which somehow make sense. So, for example, if we consider that we have this item set of milk, diapers, and bread, this milk, diapers, and bread will be somehow the rules which are associated with these 3 variables, either that milk implies diapers and bread and so on, they all have the identical support, because the support is simply calculated from the frequency of the item set in the entire set of transactions. So this is therefore characterizing this rule: milk and diapers imply bread, bread and milk implies diapers, milk implies bread and diapers, bread and diapers implies milk, bread implies milk and diapers imply bread and milk. So they have the same support, all these rules. However, they do vary in the confidence, because the confidence is the frequency of, let's say, milk and diapers, but then divided by the frequency of the set which is before the implication. So we divide it by the occurrence of the milk and diapers for this rule, for example. For this, we divide it by the frequency of milk and bread, and here of a frequency with milk. So these rules will have a different confidence while they have the same support. Now, so therefore, we divide this problem of association rule mining to two stages. One stage will be that we first search for very frequent item sets that satisfy the condition that the support is bigger than the minimum support threshold. And once we identify those, and only those frequent item sets will be then further analyzed to filter those for rules which have high confidence. So in the first step, we are actually not looking for the rules. We are looking for frequent item sets which can be behind certain association rules, and only keep those which have high support. Those will, for example, this kind of support calculating this set, our item set, will be having the possibility of having association rule of any of these 6 rules. However, maybe only very few will pass the confidence threshold, and those will be those which we are searching for and possibly want to then analyze even further. And the key algorithm which allows us to actually look at this huge item set space is the so-called a priori algorithm. The a priori algorithm allows us to see the somehow systematically traverse the item set space. Look at the all possible item sets from the letters of A, B, C, D, E. So these are already 5 items, 1 item sets. Then we have 2 item sets, which are all possible combinations of the 2 letters here, where the order doesn't matter and they are only alphabetically sorted because it's a combination. We are not really measuring permutations here. Then combinations of 3 letters is here, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, we can use combinatorics for expressing how many of these combinations we will obtain. Then 4 item sets will be 5, and then there will be 1 6 item set. So the topology of our item set space will look approximately like this. And within this space of items, there is an interesting observation. Even if this space is huge, we can potentially prune a lot of items from this huge space by classifying those item sets as not really frequent. So, and the key insight here is that the frequent item set needs to have all its subsets also frequent. So if this item set is frequent, then it must mean that these item sets above it, so C, D, C, E, D, E, must be also frequent, and also because every time when this one shows up, also at the same time this shows up, and this shows up. It's just combinations of these three letters into tuples of 2. And then we have also the single occurrences. One item set needs to be also frequent if the CDE item set should be frequent. So this is an key observation which allows us to prune this search tree. However, it's not so much informative or useful to say that this item set, if we find that this one is frequent, then all these sets are frequent as well. Because how can we, that doesn't really help us in pruning. And first of all, how do we come to the conclusion that this item set is frequent? What would be the systematic approach to that? So therefore, there is an equivalent formulation which says that if an item set is infrequent, then all of its supersets are infrequent. So it's the opposite in terms of the direction, but also in terms of the infrequency. Meaning that if A would be, for example, infrequent, then that means that everything which contains A will also have to be then infrequent because it's subordinate to the A itself. If there is very few A's, then there cannot be too many AD item sets, for example. So if those are not frequent, if those item sets are not frequent, then a subtree can be pruned. And we can see that here. For example, maybe one item set A is frequent, but maybe the AB is not frequent. And then, therefore, we can prune the ABC, we can prune the ABD, we can prune the ABE, ABCD, ABCE, ABDE, everything which contains this two item set AB will be pruned away from the tree. So with this way, we can prune already a lot on various levels. And that is the basic strategy of searching for a candidate item set as a subset of the huge item set space. And we will be traversing our tree for the a priori algorithm in the breadth-first search. There could be also other ways, like for example depth first, but we will be interested to do the breadth first because we first want to check all the one item sets and prune already those wherever possible if the individual items are not frequent, and then prune a huge subtree which is related to that, those item sets containing those infrequent one item sets. So we will proceed in this way until we basically prune the entire tree and are left out with only few item sets. We can see this in the following representation here on our transaction record example. Here we have the one item sets, and we would say that our frequency threshold must be 3, meaning that we want only those item sets which will be 3 times at occurring in the entire transaction record. Or alternatively, we could say that we are interested in a frequency which is 3 divided by 1, 2, 3, 4, 5, 6. So which is 1/2, 50%. And with that, we will be filtering already for the one item sets. And there we could see that, for example, the beer can be counted 3 times in these 5 transactions which we were having, and the bread is 4 times in these 5 transactions, so nearly in every. Then Coke is in 2 transactions only, and therefore everything will be pruned, and any 2 item sets will not be already containing the Coke. Diapers are 4 times, milk is 4 times, eggs is 1, so they will be also pruned. Therefore, we will in the second item set representation, we will have the 2 item set will be consisting of the combinations of those which sort of survived. So beer bread, beer diapers, beer milk, bread diapers, bread milk. And we will be constructing these, and so in a systematic way. So for example, we will be now only these beer, bread, diapers and milk will be sort of surviving to the next candidate for 2 item sets, and we will create 2 item sets which we will sort always alphabetically. And then we will create a systematic approach how to create 2 item sets. So the FK is a set of K item sets. Here we had a set of 1 item sets which were F1. So 2 item sets will be F2. We will be creating F2, and we will be creating them from the F1 item sets which survived. So we will make like 2 elements, but only in such a case if the K minus 2, meaning F0, will be item. So this is F2, this is F1. If K minus 2, if items are identical. So in this case, we have like this doesn't really apply for the 2 item sets in much of a logical way, but so we will create the 2 the tuples like with start with the beer and then bread, but then we will, because the E here is before R, we will have them sorted alphabetically. Therefore, we will not be adding the bread and beer, which is the equivalent combination of that, because the bread will never be added before beer. The beer will be first in the order because the item set needs to be sorted alphabetically. And then bread will be in combination with diapers, like here, but also the beer will be in combination with diapers, this is here, and beer will be combination with milk, which is here, and then bread with diapers, bread with milk, and then diapers with milk. So as you can see, this is all nicely now alphabetically ordered, and we have these candidates 2 item sets, and we can check which of these 2 item sets are actually satisfying the criterion of being at least having the support of 1/2 in our case. Well, the beer bread is counts only 2, so it's less than 1/2 because divided by 5, and then so not 6, but so it's 3/5, and this is only 2/5. So this will be then beer and diapers are 3, so 3/5, that's fine. And then we have the beer and milk, it's only 2, so this doesn't pass the threshold because it's only 2/5. And then we have bread and diapers, which passes the bar. Bread and milk also barely passes the bar, and also diapers and milk passes the bar. So now we are looking for the item sets which are 3 item sets, and now we are applying this rule where we generate it from the fk-1 and fk-1. So like we will construct the 3 item set from maybe this set and this set. However, we have a condition that if k-2 items are identical. So this means that that beer diapers, we need to have another one starting with beer and something else to create a 3 item set. So because the k-2 need to be identical, the first one would need to be identical. So this is not the case. And only in the case of bread and diapers and bread and milk, we have the case that they share the bread as the k-2 items. So this is one item, the first item is identical, and that means that we can create a 3 item set out of it, and then nothing else, because nothing else is showing up with the first item being the same, except of these two. So we have just created just one item set, so bread, diapers, milk, and the count of this is 3 times, so it passes our threshold. As we have only a single one, then we cannot create a 4 item set, and with this our process of frequent item set generation is completed. We have successfully pruned a lot of options with this in this process, and we have then finished with choosing just one 3 item set. But also we have other item sets possible, like these 2 item sets are still valid for creating association rule. However, in this case, 1 item set, there is no association rule possible because there is not an co-occurrence of 2 items where one would imply the existence of the other. So with this, we are finished, and we always, during this potential generation of the FK, we perform the support counting so that we can perform the pruning of the infrequent item sets. With this, we have finished one part of the a priori algorithm, which is this frequent item set generation. Once we have the frequent item set generation finished, we have several possible rules which we can check. As we have seen, for the 2 item sets, we can basically check only whether the support for one item set implying the co-occurrence with another item set, whether it has a high confidence, and then we have for each 2 item set entry, we can generate 2 rules, one implying the other and the other implying the one. Only for 3 item set, we will have a slightly more combinations. We have already seen that on the previous slide, where we will have 6 combinations. But generally, let's have a look at how many rules can be generated in general from k item set. In the real world data, we will be dealing with much bigger item sets and with much bigger transaction history and much larger set of items that we will need to consider the fact that the k item set will generate us in general 2 powered by k rules. So we can see how this sort of looks like for the 4 item set A, B, C, D. the 4-item set ABCD looks also like the similar graph like we have seen before, where we start with the root, which doesn't really make sense, but it's an initial root where the A, B, C, and D implies an empty set, so do not have any association. But then the first level will be that the 3 of the items, 3-item set, will be implying a 1-item set, where we are basically here varying what is the 1-item set, and the rest is in the 3-item set on the left-hand side of the implication. So these are the 4 rules which we can create from this 4-item set, implying just a single item or single 1-item set from the 3-item set occurrence. However, here again we can use the fact that that rules can be tested for confidence based on previously calculated and stored sigma and sigma functions, so that we actually do not need to now go through the entire set of transactions and search how many times do they occur, but we have it already stored, and from that we can calculate the confidence. And then for some cases the confidence might be high, and for some cases the confidence might be low. Here we are looking, for example, for the low confidence rules, because what holds is that if a rule which is x implies y minus x, so that we do not have the x expressed on the right hand side, it is the y is not containing any elements of x. If that is smaller, this confidence, than the minimal confidence, then x prime implies y minus x prime will also be smaller than the minimum confidence threshold in case the x prime is a subset of x. So once again, if on the left-hand side of our rule association, we have a set which is larger, consists of more items, a bigger item set, and then and that one is having smaller confidence than the threshold, then any other rule which has a subset of the x on the left-hand side of the implication will then also not be exceeding the minimal confidence threshold. So that means that if we identify here confidence of a rule which is low, that means that any which contains BCD, any of the combination of BCD on the left-hand side of the implication can be pruned, because also will not exceed the minimum confidence. So if this rule doesn't exceed the minimum confidence threshold, then also will not this one, and not this one, not this one, and also not this rule, and this rule, and this rule. So practically the half of the rule tree or graph actually will be pruned away, and we will be left out with just all high confidence rules, which we can then declare that they are the discovered associations in the data. So we apply in this a priori algorithm the same kind of pruning strategy as we have applied for the item set frequent item set generation, we do it also in the rule generation stage, where we prune the low confidence rules based on this principle as where we propagate downwards this low confidence to the rules which contain the subset of the left item set in our implication. However, there is just one more thing which needs to be said. With this, with this traversal of the prune tree, eventually, with the breadth first search, we will find all the association rules, and we can therefore declare those which have a sufficient support and sufficient confidence as those that can be further analyzed, and this association can be further studied. However, so they can form a hypothesis. However, there is a certain so-called high confidence trap. Imagine that if X implies Y, we find such an association, but and this association has a high confidence, but the high confidence is because Y is so super popular that it occurs basically in every transaction, then it is actually this high confidence is not because of this association rule, but because of the popularity of Y in general, overall, and not because of the relationship with X. So that high confidence trap is problematic and can really exist. So for example, if we have a rule that says that bread implies milk with 80% confidence, but milk is already in 90% of purchases anyways, then actually buying bread lowers the likelihood of purchase of a milk. So it actually doesn't have a association, positive association. It has actually a negative association. So this high confidence can actually be quite misleading, and therefore it is interesting to search for some other ways how we can discover whether there is a high confidence trap or not. And this can be found, for example, by the so-called lift, and this lift can reveal the confidence trap. And the lift is a formula where we compare the confidence of the rule X implies Y with the support of Y. And if this ratio ends up with being bigger than 1, so the confidence is higher than the support of Y, then this rule is really useful. If it is equal to 1 or smaller than 1, then this rule is not really useful and doesn't need to be selected for some hypothesis generation. So finally, after our frequent item set generation and rule generation, we should check every of the association rule whether there is a high confidence trap problem or not, and filter out those where this high confidence trap problem occurs, so that we are left only with those which are not having this high confidence trap problem, are actually real associations. So with this, we have a full understanding of the a priori algorithm on a high level. There are very important details about how is the, for example, support calculated, and for each during the traversal of this a priori item set graph or the rule graph, this needs to be performed extremely efficiently through various hashing structures and so on. But we will not be discussing these technical details which make these algorithms possible to run within a reasonable time, but we only focused in our conversation now on the essential concepts. So this a priori algorithm remains to be one of the landmarks of the association analysis. It has an interesting relationship to the search in trees, as we have been discussing at the beginning of this lecture. And with this algorithm, we basically close the loop to this search algorithms, where both the breadth-first search could be used, but also, for example, a depth-first search for a priori would be possible to accommodate. With this, we are concluding this brief introduction to association analysis, and this concludes also this lecture set on data analytics. Thank you for your attention.